Now I've got a yellow rubber band. I'm going to shoot it across the screen, see how we do. Well, that didn't go very far. Let's try it again. I was afraid to pull it back too far because I thought it might travel too far. Let's try once more. See if we can get it to go across most of it. Let's try it. Well, that went a little too far, but you saw it go up and down. Kind of hard to calibrate the thing. Okay. The rubber band followed, in both cases, pretty much a parabolic path. And that parabolic path can be modeled by a quadratic function. In fact, we're going to look at a model that gives us a parabola that looks something like this, okay? And we'll see how that comes out of the function. So this could be the path of the rubber band, or in the case of this rubber band, it actually starts right here. So this part of the parabola doesn't correspond to the actual motion of the rubber band, but then this part does. It's shot from a height up here, goes up to maximum height, and then comes back to the floor. And our model is going to be h of x, h being the height above the floor, and x being how far we've gone in the horizontal direction. So h of x is negative 0.5 x squared plus 0.8 x plus 1.32 for the particular model we have in mind. Okay? Now we could graph this in a number of ways. We could complete the square and use transformations. Completing the square, negative 0.5 x squared plus 0.8 x. We could factor this thing, but probably not. Doesn't look like these numbers aren't going to be all that amenable to any attempt to factor. You can try it if you like, you see what I mean. So we probably won't factor for this function. Or we could use the quadratic equation as a basis for the graphing. I'm going to choose this time to use the quadratic equation just to reinforce what we can learn from the quadratic equation. Okay, now, quadratic equation, we find the zeros. Now we're going to find two zeros, and we're going to see, you already see that the zeros are going to be at negative 1 and 2.6, but how did we find that? We couldn't put that down there until we found it. We plugged A equals negative 0.5, B equals 0.8, 1.32, C equals 1.32 into the quadratic formula, and this is what we get. You can do that. You should do that yourself. Just the A, B, and C for this quadratic function into the quadratic formula. It's something you've done a number of times. You won't have any trouble. You'll get this, and then when it's simplified, it turns out that we get negative 0.8 plus or minus 1.8 over negative 1. Now, there's something a little bit amiss with my numbers, and I'm going to pause for a second. Sorry for the interruption. I keep thinking this really needs to come out 3.24. It comes out 3.28 under the square root. But the way I set it up, it really should come up 3.24. I don't understand what I did wrong, but you don't need to worry about it. Okay, so we plug the parameters of this function into the quadratic formula, and we end up with zeros at x equals 2.6 and at negative 1. So we plot those points on the graph. Then what do? We find the point halfway in between. That's going to be our axis of symmetry, halfway between the zeros. So the axis of symmetry is going to then be, well, halfway between negative 1 and 2.6 is negative 1 plus 2.6 divided by 2 gives us 0.8. So x equals 0.8 is our axis of symmetry. We plug 0.8 into our function when x equals 0.8. I'm not going to read it to you again. You can do it yourself just as easily as I can. We plug in the 0.8, we evaluate it, we get 1.64. So the 1.64 is the highest point on this graph. Now, this graph represents the path of that rubber band, so that's how high the rubber band is going to be at its maximum distance above the floor. Also, it's going to travel 2.6 meters before it reaches the floor. Now, this graph doesn't do a really good job of representing the relative scale. If this distance is 1, this distance isn't 0.8. Okay, I didn't do a good job of locating the y-axis, so I'm going to redraw it. I've got my -1 here, my 2.6 here, and my 0.8. That's 1.8 units from 2.6 and 1.8 units from -1. Now, if -1 here is here and 0.8 is here, halfway between those, you can calculate easily, would be -0.1, so that the y-axis probably goes about here. So I'm going to put the y-axis here, or the h-axis, since this is h. Label that h of x. And then I'm going to redraw the parabola. Its maximum is going to occur here, and that height will represent the 1.64. And if I draw a nice parabola, peaks at this point, comes back down to 2.6. That's not a very well drawn parabola, but we see that this distance here, this is supposed to be 1 because this is 1.32. H of 0 is 1.32. Well, that makes pretty good sense on the scale. So what's happened is the rubber band has been released at the point 1.32 meters above the floor, and it travels this path, reaching the maximum height of 1.64 meters, traveling 2.6 meters before reaching the floor. And the actual path, I'm going to kind of write over this in blue, the actual path will be kind of like that blue curve. In blue, I've indicated that the blue path is the path of the rubber band shot from the point 0, 1.32.